Okay, so I'm recording now. Let's look at this answer. I asked you guys to take a few minutes to try this. Let's look at this answer. Then we'll move into redox or oxidation reactions. We call them redox. I'll explain why, and then that'll be it for today. So first things first, total ionic equation. Anything, oops, anything that's aqueous, we write as ions. So we split them apart into cation and anion. Anything solid, liquid, or gas, you do not touch. So two aluminums, you don't actually need the coefficients here, but I will put them in. So two aluminum solid plus three coppers. Copper would be 2 plus in this case. Whoops. Plus 6 chlorines. We have 3 molecules or 3 ionic compounds, and there's 2 in each. So that's 6. Then I get 2 aluminum 3 pluses, another 6 chlorines. So I notice that there's 6 chlorines on both sides. So that to me looks like a spectator ion. And then, oops, my 3 copper solids. Okay, so step number 1 is to split the ions from, or split aqueous solutions into ions. Step number 2 would be to cancel your spectator ions. Spectator ions are any chemicals that appear on both sides. So the chlorines, goodbye, they are gone. This means my reaction is going to just be 2 aluminums plus the 3 copper ions, copper 2 plus ions, whoops, goes to 2 aluminum ions plus 3 copper. Sorry guys, my pen's going a bit weird here. Okay, there we go. 3 copper solid. Now, this reaction is a single replacement. All right, and actually what this reaction is a great example of is the next topic. We're almost on chapter 5. We'll get pretty close to finishing that chapter tomorrow, and then hopefully in Monday's class, we can finish chapter 5. So this is our next, kind of leads into our next section. This is a good example of something called a redox reaction. So a redox reaction, which is what I'm going to look into now, involves a change in oxidation number when chemicals charges change. Let me just check the chat there. Nope, there's one more unit after 5, but unit 6 should only take a class or so. Unit 6 is very short. It's about gases. So it's just one, I think it's only maybe 20 slides in unit 6 instead of like 100 slides in unit 5 or like 150 slides in unit 3. Unit 6, very short. Should only take us about a class. Yes, and the final is all 6 units. So we'll talk a little bit more about your final exam next week. All right, so oxidation numbers. Again, let me go back 2 slides here. This is an example of this type of reaction I'm about to talk about, called oxidation or redox reactions. To look at a redox reaction, you need to look at the charges of elements in a chemical reaction. The oxidation number is a very fancy way of saying charge. Charge is, we did this back in chapter 3. It's like the numerical value on, say, an ion. So aluminum 3 plus, copper 2 plus, oxygen 2, excuse me, 2 minus. Oxidation numbers or charges, again, it's the same thing. They tell us how electrons move in a chemical reaction, and typically they range from -4 to +7. So on our periodic table, we don't see many charges or oxidation numbers smaller than -4 or bigger than +7. So how do you find the charge on atoms? Well, there are 4 rules. Now, this is a little bit different than chapter 3, because we're going to look at this a little bit more in depth, meaning it's a little more complicated when we deal with molecules. So there are 4 rules or 4 steps you follow when you're finding the oxidation number of a compound. The first rule is, and you have to follow these rules in order. So the first rule, if the chemical is an ionic compound, split them into their ions, just like we did in chapter 3. When we named things in chapter 3, we had to split them into their ions. So we knew, for example, that something was like iron 3 chloride, not iron 2 chloride. So we did that in chapter 3. But it does get a little more complicated. The next rule is that the sum of all of your charges in a compound is equal to that compound or charge. And I'll explain this one in a minute. So this one sounds confusing, but I will get to that in a minute. Rule 3, the oxidation number of hydrogen would be +1 in a molecule. And rule number 4, the most electronegative element's oxidation number is its ion's usual charge. That typically applies to oxygen or fluorine when there is no hydrogen. So this can sound a little confusing, but you'll see me kind of go through my rules here and solve some examples. So I have 3 examples here, ranging from easy to difficult. I have an ionic compound on the left. I have a ionic compound in the middle with a polyatomic ion. And then on the right, I have a molecule. So we have to follow our rules differently for each of these. So step number 1, split your chemical into ionic compounds if possible. So example number 1 on the left, lithium fluoride, very easy. Lithium is +1, fluorine is -1, we're done. That chemical is finished. The middle chemical, nickel 2 chloride, nickel and nickel 2 carbonate, we split it into its ions. We have nickel 2 plus and we have carbonate, CO3 2 minus. NH4 is covalent. It's a molecule. So it's not ionic. I can't do step 1 there. So I'll move into step 2. Step 2 says that the charge of the compound must equal the oxidation numbers, the charges of the elements in that compound. So what do I mean? Well, I know lithium, I know fluorine, I know nickel, but carbonate and NH3, I do not know. So carbonate, I know that if I add the charge on carbon and I add the charge on oxygen, 3 oxygens, it must equal -2. So I'm basically creating a math equation, an algebraic expression. Now, where did that -2 come from? So what's up with this? Well, carbonate is CO3 2 minus. This must mean that if I added the charge of 1 carbon to 3 oxygens, it would be -2. Ammonia, I can do the same thing. 1 nitrogen plus 3 hydrogens must equal 0. There is no charge overall, no charge. I should say overall on the molecule. Okay, no overall charge on the molecule. All right, let me check the chat. Abdul Halim asks in the chat, how do I know that CO3 is 2 minus? In your data booklet, just like we did in chapter 3. If you remember chapter 3, when we did naming, it's on your polyatomic ion chart. in your data booklet. That looks like date book. There we go, data booklet. Okay. Excuse me, we will practice this, of course. Okay, step number 3. If there's a hydrogen there, the charge on hydrogen is +1. If there's no hydrogen, move to step 4. So, do I have somebody, I can hear somebody's microphone. Is there a question? No question? Okay. So, step number 3, the oxidation number of hydrogen, if it's there, is +1. If there is no hydrogen, go to step 4. So nickel carbonate here, there is no nitrogen present, so I need to go to step 4 for this one. This one on the left is a little challenging. Ammonia, however, there is a hydrogen. So I have my math equation, my little algebraic equation here that I created in step 2. Nitrogen plus 3 hydrogens has no overall charge. So I put in +1 for the hydrogen. So nitrogen plus 3 times 1, or nitrogen plus 3, equals 0. And then I just solve for nitrogen like you would do in math. Again, this is just algebra. It's not chemistry. So hopefully you guys are pretty confident or strong in simple algebraic expressions. There's no, square roots or exponents or logarithms here. It's just straight adding and subtracting. Okay, so we still have to worry about the carbonate. So the last one, if there's no hydrogen and you've made it to step 4, the most electronegative element takes the charge that it normally has from the periodic table. We're going to practice this, by the way, guys. So typically, wink, 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 in chemistry 1120 or even chemistry 1121, it's typically fluorine, or more specifically, oxygen. Most of these compounds we'll look at have oxygen. Oxygen is -2 and fluorine is -1. And again, remember, we have to do our rules in order. So this applies when we've made it to step 4. Yeah, so Aman has a good point there. You can know N from the periodic table without doing math. That's correct. But some compounds, it gets a little more challenging. And you'll see that in my examples in a few minutes. Sometimes N will not be -3, or sometimes you'll have to look at, like in this example, carbon. Right? Carbon, we don't know the charge of carbon on the periodic table. Not really. So you can look at this here. Okay, so my equation, my mathematics is 1 carbon plus 3 oxygens equals -2. So I put the oxygen in. I have a -2 here. So carbon minus 6 is equal to -2. Solve this equation. Carbon is +4. Woo, pretty challenging. It's easier than it looks once you practice this, but it can appear to be a little bit challenging for sure. So let's do this together. I have 7 examples that we're going to look at. This is typically a little easier in practice, by the way, when you see the next part, the finale of today. We're going to look at, what do we do with these numbers? What's the purpose of these numbers? So let's do this. I'll do a few of these. I'm going to show you especially, some of the harder ones. But let's do these together. I'll do most of them. A doesn't fit into any of our examples. A is just an element. It's not a compound. If it's an element, no charge. Okay, that it doesn't fit into any rules. It has to be a compound. So if it's an element, there's no charge here. So the charge on sulfur would be 0. No charge. Okay, elements do not have charges. Compounds have charges. Elements do not. And I'm saying charges a lot. I really mean oxidation number, okay? We learned in chapter 3 charges were for ions, for ionic compounds. So what do we do with molecules? Well, we call them oxidation numbers. Okay, so let's look at B, C, and D. D is a weird one. D is an exception to most things because you'll see what happens with oxygen in D. And that D will kind of bring me back to what I said to Aman. We know most charges from the periodic table, but you'll see that it's not always true in a compound. Okay, so B is ionic. We can just do step one, right? Potassium is always +1, Br is -1. That's it. It's just an ionic compound, no problem. C is also ionic, and I don't need to worry about rules 2, 3, or 4. I can just do rule 1 for C and rule 1 for B. Very simple. So in C, sodium is, of course, +1. Hydrogen, in this case, would be -1. Now, I know if you look at the rules, it says hydrogen is +1, but that's as you go through the rules. You have to do them in order. For questions B and C, it is ionic, pure ionic compounds. So I don't need to do rule 2. I don't need to do rule 3, which says hydrogen is +1. So I can move on. Now, in this one, I'm going to have to do rule 1, 2, and 3. Just give me 1 second here. I have to let my dog in. If you want to try D, you can, but I'll be back in literally 10 seconds. I just have to open the door. Just 1 second. Okay. So back to this question, rule or question D, rule 1, 2, and 3. I guess arguably for question C, guys, I was just thinking about it as I walked over to the door. You could apply rule 2 here, right? So I know that sodium is +1. So sodium plus hydrogen has to equal 0. +1 plus hydrogen equals 0, which means hydrogen in this case has to be -1. Okay, you could use rule 2 there. I mean, you could even use rule 2 for question B, but the idea is, potassium plus bromine has to equal 0. The charges must cancel in ionic compounds. They must. Okay, so question D. This is a tricky one. This is one. Oh yeah, actually, well, sorry, Iman makes a good point, but yeah, this is a tricky one because it's an exception to oxygen. Oxygen, we know from our periodic table that oxygen is mostly -2, but you're going to see what will happen with this compound. This compound is called hydrogen peroxide. So some of you guys might have this in your house right now. Uh, it's an antiseptic, I think, or disinfectant you can put on cuts and things. I don't know. I don't really ever use it. I know it helps kill mold in plants, but a lot of people keep hydrogen peroxide in their like bathroom or first aid kit. This is an interesting one. So Aman mentioned in the chat, well, we can't use rule 1 because it's not ionic. And you're right. Like what I mean here is we're going to you always look at your rules in order. So rule number 1, is it ionic? Nope. Move on to rule number 2. Rule number 2, the sum of all of these elements must equal the charge on the compound. So, you're right. I'm not using rule 1, but I have acknowledged that rule 1 doesn't apply. So I skip to rule 2. 2 hydrogens plus 2 oxygens equals no charge. Again, how do I know that this has no charge? Because there's nothing written up here. If this had a charge, it would be written, but it doesn't have a charge, right? It doesn't say 2 plus here. It doesn't say -1 here. There's no charge on this. Okay, rule number 3. I have hydrogen here, so I'm going to put in +1 for hydrogen. Rule number 3 states that if there's hydrogen in this compound, call it +1. Then I add 2 oxygens, and I know that that equals 0. So 2 plus 2 oxygens equals 0. 2 oxygens would equal -2. well, I don't really need to review algebra, or I shouldn't have to review algebra, but if you have trouble with algebra, make sure you we'll make sure you know it. I know that sounds really weird, but that's a math question, not a chemistry question. So if any of you need help with algebra, you can let me know. I can help you after class or something. I used to be a math teacher, so I can explain in an after class, but I'm assuming most of you know how to solve for X, for example. So in this case, hydrogen is +1, oxygen is -1, which is weird because oxygen is usually -2, but not if we follow our rules. Okay, let me do one more, and then I'll give you guys a minute to practice, and then we're almost done for today. The thing I want to do today before I finish is I want to show you why this is important. Why are we learning this? All right, so let me do one of these. I'll do F, and then I'll get you guys to try E and G. Now, I'm giving you difficult ones. They're usually not this difficult, as you'll see in the next couple of examples, but let's do F. Okay, so rule number 1 for F is I would split this into its ionic compound. It is ionic, but it does have a polyatomic ion on it. So this would be Na plus and NO3 minus. This is from your data book. If you don't know this, it's in your data booklet. It's a polyatomic ion. Okay, so rule number 1 is done. I know the charge on sodium is +1. What about this guy? Well, I'm going to go to rule 2. Rule 2 says write this as a mathematical formula. I'm going to move it up a bit so I don't run out of room. So nitrogen plus 3 oxygens would equal -1. Okay, pretty good. Rule number 2, or 3, sorry, rule number 3, if there's hydrogen present, it's +1. There's no hydrogen here. So rule number 4, if you have oxygen or fluorine, call them what they are, -1 or -2. You always give the most electronegative element the charge that it normally has on the periodic table. It kind of wins the fight. So like the most electronegative says, you know what? I'm going to be -2. You figure yourself out. So nitrogen plus 3 times -2 equals -1. Nitrogen minus 6 equals -1. Nitrogen is +5. So, right, like again, going back to what Aman said, typically, yeah, we can use the periodic table. Nitrogen is usually -3, but in this case, strangely enough, it's going to be +5. So my charges are sodium positive, nitrogen, is +5, and oxygen is 2-. All right. Now I got a question or I have a comment in the chat. I don't know if it's a question yet. Okay, I'll talk about that in a minute. So one thing, I would like for you guys to try question E and question G, but Aman mentioned rule number 2 is always equal to 0. No, you can see in rule number 2, when I applied rule number 2 here, it equaled -1. Rule number 2 is that the sum, when you add all of the elements in a compound, it's equal to the charge on that compound. So in this case, my charge was -1. Let me get my highlighter. So in this case, my charge was -1. So I set my equation equal to -1. Okay, I hope that makes sense. Remember, guys, these are difficult. These are not typically how you would see this. So yeah, good luck and try E and G, and I will be back in 1 minute. You can put your answers to E and G in the chat if you wish. Okay, so I'll be back in maybe 2 minutes, and then we're almost done. I just got one little quick thing to show you and we're finished. So yeah, 2 minutes. Recording, let's go through the answers. I would love to give you guys a little more time, but I need to keep you on pace with the other class, and they got into the next section. So I have to move on very quickly, but don't worry, I'll take my time. And that's good. I'm glad. Iman mentioned that you started to figure it out, and really, it all like. I know this is such a teacher cliche to say, but it's like you really don't know it until you try it, and then if you try it, you can start to figure it out. It's not as bad as it sounds, or looks, I should say. All right, so let's quickly do the answers here. um, I'll introduce the next section, which is really the application of this. And then that's it for today. And we're almost done. I think after today, we'll only have about 20 slides left for chapter 5, which should only take maybe a couple, like a class and a half, maybe. So we're getting very close to the end. Kind of scary, kind of exciting as well. All right, so this compound, let me switch to my pen here. Okay, this compound. Well, it's definitely not ionic. So I'm going to go to rule 2. 2 phosphoruses plus 5 oxygens equals 0. You'll notice I put a line through the 0. That's just so you know that it's not oxygen. That's more for my brain than you. Zeros and O's are the same thing. So, well, they look the same. So this line here just means that it's a 0. Helps me make sure I know it's not oxygen. Okay, so rule number 1, it's not ionic, doesn't apply. Rule number 2, we can do that. I just did that. Rule number 3, is there hydrogen? No. Rule number 4, oxygen or fluorine would take their own charges. You guys won't see anything ever in chemistry 1120 or 1121 outside of oxygen or fluorine. Like, trust me, I've taught them all. I've seen it all. So I have oxygen here. So 2 phosphoruses plus 5 times -2 equals 0. 2 phosphoruses minus 10 equals 0. And I'm out of room here, but you can trust me when I say that this will be positive 5. And oxygen will be -2. Okay, so the charge would be 5 plus and 2 minus. In the chat there, I have a question. It says, yes. So Abdul Halim answered that. Yeah. So you guys, you're the best. I'm gonna miss you guys when we're done, I must say. I mean the whole class, but I'll definitely miss you guys. So the question was, P2O5 is not in the data booklet. So how do I know it's 0? Why is it 0? And Abdul Halim answered that perfectly. When I write this for you, if I don't put a charge on the top of it, it's 0. So like, for example, if I gave you water, H2O, well, there's no charge on this. It's a neutral compound. So 2 hydrogens plus 1 oxygen would equal 0. If I gave you, N2H6, 2 nitrogens plus 6 oxygens would equal 0. There's no charge. If I give you a chemical that doesn't have a charge, it must equal 0. Okay, so let's look at the last example. I do have to move on because I do want to get you into the next section. I just have to keep you up to pace with the other class. So just give me a few more minutes here. The last example. Okay, rule number 1 we can do. This is definitely an ionic compound. Now, I would look in my data booklet. I know that ClO4 is 1 minus. I don't actually need my data booklet here, though. I know that lithium is +1. So this compound, the anion, must be -1. Unfortunately, I need to figure out the charge on this compound. So 1 chlorine plus 4 oxygens would equal -1. Chlorine plus 4 times -2 equals -1. Now I'm using all my rules. So rule 1, it's ionic, so I split it. Rule number 2, it's I add up the atoms and it equals -1. Rule number 3, there is no hydrogen, so I move on. Rule number 4, I put in -2 for oxygen. So Cl minus 8, not 7, equals -1, and then that means when I solve this, Cl is +7. So as in chemistry, we would write it like this. Lithium is positive, chlorine is 7 positive, very big, and oxygen is 2 minus. Now, you guys know that your final exam is on campus. I don't care how you write these down. I'm the one going to mark your final exam. So, if you put a plus here or if you write 7 positive or positive 7, I don't care. I'm not that picky. All right. Last part. Now, I know it's 3:15, so just give me a minute here. I'd like to just maybe show you an example, and then we'll practice the other ones tomorrow. Okay, so just give me, no matter where I am, I will finish at 3:20. So 3:20, I'm going to finish. What is the point of this? Why am I telling you this? Why do we have to do all of this work to find oxidation numbers? Well, you'll learn more about this if you go to Chemistry 1120. Chemistry 1121. Chemistry 1121 has an entire chapter called electrochemistry. Electrochemistry is exactly what it sounds like. It's the chemistry related to the transfer of electrons. It's the chemistry related to electricity. It's how batteries work. You guys, there's not a moment in your life where you probably don't depend on a battery. There's a battery in your remote control for your TV. There's a battery, excuse me, in your car. It wouldn't start without a battery. In your vehicle. There's a battery in your pocket probably, or in your purse. Your cell phone has a battery in it. Your computer, your laptop, they all have batteries. Batteries work on electrochemical reactions. So what happens is when a chemical reaction like this one happens, oxidation numbers change. We call this a redox reaction. Redox is a combination of the word reduction and oxidation, and you'll learn a lot more about oxidation and reduction in Chemistry 1121. But in simple words, when a reaction changes its oxidation number, electrons are moving. When electrons move, that's what electricity is. As far as I know, Naval, next semester in the winter, I am teaching Chemistry 1121. So you guys might see me. You might have me next year. I hope so. I'd love to have you guys again. And I mean that, I've had some bad classes before, but I'd really like to have you guys again. So inshallah, we'll see what happens next year. But I am teaching 1121 in the winter. Okay, so basically the idea is, and I really don't have time, which is unfortunate, but the idea is you write the oxidation number for all of the elements, and if the charge of something changes, so like guys, look at the purple and orange. Let me get my highlighter here. Look at the orange, look at the purple. If you see in a chemical reaction that a reactant has a different oxidation number, a different charge than a product, this is an electrochemical reaction. Electricity or electrons are moving. You can use this, and in 1121, we will do this. And I'll say inshallah, because I hope COVID or Corona is calmed down next year. I hope there's a vaccine. Because in Chemistry 1121, in the lab, we will make a chemical reaction power like a light bulb. Like, it's really amazing. You can mix two liquids together in a special way, connect wires to these liquids in a special way, and you can power a light bulb. You can charge your phone. It's amazing. And all you do is just take two chemicals, mix them together. Very cool. So this is a redox reaction. Examples of redox reactions are like rusting or corrosion. This is good for my engineering students. Oops, I didn't mean to have that there. So my engineering, even I guess my medical science students, you would deal with rusting or corrosion of metal equipment, maybe in the hospital. I know my engineering students, you'll definitely be learning about rusting or corrosion because it's a huge problem in the industry. So what we'll do, I'm out of time, it's 3:20, but tomorrow we're just going to see if these reactions are redox. This is an example. You guys can look at this if you want to. And then we'll do these two tomorrow. And I'll give you a hint. One of these is a redox. One of these is not. Okay, you can try this. I mean, you already have the skills to do this. What you would do is you would find the oxidation number of every element and then see if they change. Okay, this one's even easier, right? You just have to find it for 4 things. And if they change, it's a redox reaction. If they don't change, not a redox. Not every chemical equation has the charges changing. Yeah, and yeah, like lemon's a good example of acid. Actually, fruit and vegetables in general are a good example of redox. This is my last thing, and then I'm done. When you cut an apple or a banana or an avocado in half, and you notice that they turn brown, in the food world, they call that oxidation. And it is a redox reaction. Things are happening with the molecules, the chemicals in that food, that when it's exposed to oxygen, it changes color. Color change is a chemical reaction. So an apple, banana, avocado are great examples. Even a lemon, when you cut these things, you're exposing them to oxygen and things happen. But I think you might have meant lemon like acid corrosion, which is true. Acid and lemons can react with metals. Anyways, guys, I went on a little long today. I don't know how I go faster in the first class, but I typically do. So we'll get back into this tomorrow. Have a fantastic evening. If there's any questions, let me know. If there aren't any questions, have a great day.